Hi, today we're going to talk about our third physics lab, which is going to be about the calculation of black hole mass using the star's trajectory around the known black hole. So, in order to do that, we're going to need to talk about several concepts, such as the gravitational force between two objects formula, which is noted as G, a gravitational constant, is times m1 times m2 over d squared, where G is equal to 6.67 times 10 to the negative 11 meters cubed over kilograms times seconds squared. Next of all, we're going to need to talk about the momentum formula, which is equivalent to P is equal to m times v. And you're going to use that momentum formula to calculate dp dt, which is another variation of Newton's second law. Before we start our actual calculation of the black hole mass, we will need to make some predictions, in which my prediction would be that the mass of the black hole will be greater than the mass of the star, since the star is orbiting around the black hole. Before we begin our actual iterations through the VPython code, we're going to need to introduce all of our initial conditions that were given to us, such as the mass of the star, which is 1.989 times 10 to the 30 kilograms, and the change in time, which is delta t, which is equal to 86,400 seconds, or equivalent to 1 day. Next, we're going to use the given data from the given CSV file and calculate the x component and the y component of the velocity formula, which is denoted in this piece of code right here. And while that code is iterating through the loop, it's going to use that data and help calculate the v initial vector and the v final vector over here. Now we're going to calculate the initial and final momentum by plugging in the corresponding initial velocity and final velocity, and then we're going to calculate the difference in momentum by subtracting p initial from p final and change in velocity by subtracting v initial from v final. Now we're going to calculate dp dt parallel by calculating d mag p dt, multiplying that with p hat, and then we're going to allocate this variable to f net parallel, and then we're going to calculate dp dt perpendicular by subtracting dp dt minus dp dt parallel, and then we're going to allocate that variable value to the variable of f net perpendicular. Normally, in order to calculate dp dt perpendicular, we would have to use this formula, the magnitude of p times the magnitude of velocity over the kissing circle radius. But however, because we don't have the kissing circle radius, we're going to have to stick to the notion that we're going to find this part by subtracting dp dt parallel from dp dt. Now, after allocating each of the dp dt values to their respective fnet variables, we're going to use those variables to help create a visual representation of the magnitude and direction of each of those forces when the star is orbiting around the black hole. After running the VPython code, this is what the orbit looks like. We see that the black hole is located towards the edge of the elliptical trajectory of the star, and that fnet is always pointing in the direction of the black hole. So that was the trajectory of our star orbiting around the black hole. Now we're going to actually calculate the mass of the black hole. In order to do this, we're going to use the original formula that we introduced at the beginning of this presentation, which is going to be the formula of the gravitational force between two objects, which is noted as G times mass 1 times mass 2 over distance squared. We allocated G to be 6.67 times e to the negative 11th over here, and we're going to calculate the distance between the two objects, which is going to be denoted as star dot position minus black hole dot position. And then we're finally going to rearrange the formula such that black hole mass equals to the magnitude of fnet times the magnitude of the distance squared over the gravitational constant times star dot mass. So now we're going to actually run the code to find the mass of the black hole, and which happens to be about 3.38 times 10 to the 31st kilograms, which is about 10 times larger than the mass of the star, which is denoted in the beginning, which happens to be 1.989 times 10 to the 30th kilograms. So now we're going to go on to our questions. The first one which asks, discuss the difference between fnet perpendicular, fnet parallel, fnet, and delta p delta t perpendicular, delta p parallel, and delta p delta t in general. Mathematically, they are equivalent. However, all the respective forces are responsible for the respective momentums because each of the accelerations accept the velocity derived in each of the momentum. Now for the next question. To answer this question, the answer would be no, because the only force that will be affecting the trajectory of the star is the gravitational force of the black hole, which was given to us. Because if it is the same trajectory, then the force would have to be the same. Because if the mass of the star would mass of the black hole was larger, then the star will be orbiting closer to it, since it would have a larger gravitational force, or it would be orbiting further away if it had a smaller mass from the black hole. So because it's the only force acting on the star, we can assume that there will be no difference, and it will be impossible to tell the difference between the two. So as a result, as concluded and reinforced from my IVPython data, the mass of the black hole is evidently larger than the mass of the star. In fact, it's about 10 times larger. Thank you.